Okay, this is my second attempt at making this video. Um, I'm not sure if you guys know this about the new iPad Pro, but there's a setting on it. It's sort of an artificial intelligence setting, and it gives you advice. And so when I had finished my video, and it was kind of long, I hit save, and then it paused for a second, and it said, "Are you sure you want to save this crap?" And I said yes. And then I waited about 10 to 15 minutes for it to sort of publish to my photos gallery, my video gallery, and it came back and said that the file was deleted due to incoherent rambling, and are you just do another video, it told me. So you know what? I paid money for this iPad, so I'm going to take its advice. I'm going to redo the video, and hopefully it will accept it this time. So here we're doing 8. This is the conservative force. A couple things I want to point out here, which is a conservative force is a force where the energy is conserved, meaning that all potential energy is transformed into kinetic, or the potential energy that's transformed into kinetic energy does so with no energy loss. So there's no friction or anything like that. So if for example, you lose 10 joules of potential, then that means that the kinetic energy gained 10 joules. Friction is a non-conservative force because it takes energy away from a system. So first thing first is that's the definition of a conservative force. The other thing I want to point out before we begin is that potential energy is, back in ye olden days, was called capital U. And so a lot of times if you look in older books and older AP tests, potential energy will be referred to as a U, and kinetic energy is KE, or sometimes even K. So that's just a couple of things I want to point off going right off the bat going into this question. Okay. So in general, when we have a it looks like a friend wants to play chess, but you know what? You're gonna have to wait nighty night tonight. So anyways, when you look at a graph like this, it's important to understand what's happening here, which is that we don't know what the system exactly is. This is just simply a graph of its potential energy with respect to x. And if it sounds weird or strange or contradictory that the potential energy of a system is a function of x, because maybe you're thinking that MGH, well, there's no x in there, right? So how can the potential energy be a function of x? Well, it's not that hard if you think about it. I'm just going to draw a simple example here. Imagine that you're on a country road that goes through some hills and some valleys like this, all right? So your car is going like this, up, and here you can see that your potential energy is constantly changing as you travel down this road in the x direction. So even though potential energy is not a function of x, you can definitely see that there are circumstances where h could be a function of x. And so we don't get confused or weirded out by the fact that we have a potential energy that varies with its x position. So that's sort of the way we want to start this. Okay, on to the problem. A conservative force acts in the x direction on a particle with mass of 2 kilograms to produce a potential energy curve. Okay, so the particle is released from the 0.5 meter position, which is right here. So let's just imagine that the particle is released right there. And notice it's released at rest. So at this position right here, and I'm going to stick with the way that's described. I'm going to stick with U. U is 5 joules at this particular position, and the kinetic energy is 0 because it was released at rest. So from now on, remember, this is a conservative force, no energy loss, which means that from now on, the entire system must always maintain a total energy of 5 joules. Right, it's just so conceptually, we got to start with, kind of setting the boundaries for what we're imagining this system to be. So another thing we can now just look at, again, I'm veering away from specifically question A to just teach this idea of a graph in general. Now, if the total energy has to always be 5, let's just take a look at this spot right here, just for example. Now, this potential energy is 3. So the difference between 5 and 3 must be the kinetic energy, right? Because it's a conservative force. And now you can actually get a sense of what's happening with the motion. Here you can see there's a certain amount of kinetic energy. I'm just going to call this relatively slow. Here you can see that the difference between the kinetic energy, the total energy and the potential energy is greater. So this kinetic energy is going to be relatively fast. But this position right here there is the greatest difference between the total system and the potential energy. So whatever's happening, this would sort of be the speed, relative speeds of the object, right? The kinetic energy here would be the fastest. So again, that's just a way we just sort of want to just conceptually get a sense of what's happening right here. So let's erase all that. And hopefully my iPad approves of how I'm describing it this time. Okay. So what's the potential energy of the particle at this one? Well, let's just knock that one out of the park. That's just 5. Okay, let's move on. What's the velocity of the particle at x equals 2? So x equals 2 is right here. So let's take a look at this difference between the total energy of the system, remembering that this difference has to be the KE. So shrink it a little bit. So the change in the potential energy has to be the total KE, again, because this is a conservative force. And so this would be PE final minus PE initial equals the KE, which, remember, this is because it starts at rest. So any change has to all the kinetic energy has to come from this change. So we're going to have a negative 3 minus 5. That's going to be negative 8. So if the potential energy loses 8 joules, that means that the kinetic energy must have gained 8 joules, right? That's the conservative part of this whole thing. So if kinetic energy gained 8, that means it's 8 is equal to 1/2 mv squared, the m was 2. So you can see that the v will be the square root of 8, which I believe is 2.83 meters per second. I did this one earlier, just double checking. Yeah, 2.83. Okay, so that takes care of that one. What's going on with the particle at x equals 4? So let's jump back up here and let's switch to green. So what's happening to the particle right here? Well, the first thing we're going to look at is we're going to erase this stuff. Okay, so and then I'm going to zoom in a bit here. Notice that the potential energy, I'm really kind of, by the way, I'm just going to look at what's happening around this position right here. So what's happening is the potential energy here is increasing until it reaches like a local maximum, and then it begins to decrease again. So one of the ways you can imagine this, and again, we don't know that this is the scenario, but you could imagine it, what if this is an object moving up a small hill, a small local hill? It reaches a local potential energy maximum before the potential energy starts to decrease, and it starts to speed up as it rolls down the hill. That could be what's happening here. Maybe that helps to imagine it. The fact that the whole system had 5 joules of potential means that it is definitely still moving here. So there's definitely some KE at the top. The way we could describe this is there's a couple technical ways we could describe this. This right here is called an unstable equilibrium, meaning that the object right here, as it passes the equilibrium point, the forces are not pushing it back towards equilibrium. The forces are pushing it away from equilibrium, pushing it down this way. My iPad just fell. That's why. Okay. You could compare that. You could compare that to a stable. Imagine that a marble was in a bowl. As it passes equilibrium, the forces would push it back towards equilibrium, and as it rolls on this side, it would be pushed back here. That's called a stable equilibrium. This, however, would be an unstable equilibrium because the forces are trying to push it away from equilibrium. And so you can imagine that this object, if we were to describe its motion, we would say that it reaches a local max of potential energy, but moves past it because of its velocity vector, because it has velocity past it. And that's due to the fact that it's an unstable equilibrium point. Now, obviously, if this was an AP test, you would write more than this, but I'm just trying to get these videos done in less than 15 minutes. So this is how you could describe it, that it reaches a local maximum of potential energy, but it's an unstable equilibrium point, and since it has velocity at that moment, it moves past it and continues along its way. Does the released particle reach 7 meters? Let's go back up. Now we're looking at this position right here. Does it reach this position? Well, what's happening at this position is that it certainly has Ke at this position. It was rolling up again. This could be a situation that looks just like the graph. It could be a situation where this object is going up maybe a plateau, a hill that flattens out at the top. It reaches this local maximum of potential energy and then just maintains that potential energy as it rolls across this plateau. The key here is that it does have kinetic energy when it gets up there. You know it has kinetic energy because the original system, or the total system, has 5 joules of energy, and only 3 is being used up by the potential. So yeah, it's moving past it. So does it reach the 7 meters? Absolutely. However, notice that the change in potential energy is 0 right here. Right? There's no change in this potential energy, which means that the change in Ke also has to be 0. Right? The amount of kinetic energy is not changing. So, okay, just double check. Yes. Yeah. It describes the particle's behavior. So the object at 7 is going to move at a constant velocity. So yes, it reaches, moves at a constant velocity. Ugh, that was ugly. The last question for this video is a second particle of mass m is released and it's released from rest at x equals 8. What's the behavior of this particle? Okay, so let's jump to blue for this one. The particle is released right here at rest. So this is going to differ from the original system where it was released right here at rest. Now it's released right here at rest, meaning that its maximum energy that it could possibly have is 3 joules. So its potential energy at that moment is 3 joules. Its kinetic energy is 0 joules, which means that if there's no change in potential if there's no change in potential here, there can be no change in the kinetic energy, which means if it starts at rest, it stays at rest. Right? It's not gaining any potential because there's no change. There's not gaining any kinetic because there's no change in potential. So what's happening? It stays motionless. Okay. So that is the end of the first video because C takes quite a bit of time. So I'm going to end the video right here.